In experimental design, we frequently encounter situations where maintaining uniform conditions across all experimental runs is simply not feasible. This is where blocking becomes essential. Blocking is a strategic technique that allows us to isolate and remove known sources of unwanted variation from our experimental framework. By partitioning our experimental units into homogeneous groups or blocks, we can control for systematic differences that would otherwise confound our results. Beyond this primary benefit of noise reduction, blocking also serves a secondary but equally important purpose. It extends the generalizability of our findings. When we deliberately block across different categories of experimental units, our conclusions become valid across a broader inference space, making our results more robust and applicable to real-world scenarios. As we move forward, we'll distinguish between two fundamental motivations for implementing blocking strategies in our designs. We now distinguish between two fundamental motivations for implementing blocking in experimental design. First, blocking becomes necessary when uncontrolled sources of variation would otherwise compromise our results. Consider day-to-day environmental fluctuations or batch-to-batch differences in raw materials. Without blocking, these nuisance factors could systematically bias our treatment comparisons. Second, blocking serves a strategic purpose when multiple categories of experimental units exist. By deliberately including diverse unit types within our blocks, we extend the generalizability of our findings. Rather than conclusions limited to a single unit category, our results now hold across the full range of practical conditions. This distinction matters because it shapes how we design and interpret our experiments. In the next section, we'll examine a classification framework that organizes our strategies for handling nuisance factors, distinguishing between those we can control and those we cannot. Having established the two primary motivations for blocking, we now turn to a systematic framework for addressing nuisance factors, those sources of variation that can compromise our experimental conclusions. A nuisance factor is any variable other than our treatment of interest that influences our response. The critical question becomes, what do we do about it? We can classify nuisance factors along two dimensions. First, is the factor known or unknown to us? Second, is it controllable or uncontrollable in our experimental setting? This 2x2 classification yields 4 distinct strategies. When we face known and controllable nuisance factors, blocking is our preferred approach. For known but uncontrollable factors, we employ analysis of covariance to adjust our results statistically. When factors are unknown, whether controllable or not, randomization becomes our primary defense, distributing their effects impartially across treatment groups. Understanding this taxonomy allows us to select the most appropriate strategy for each experimental challenge we encounter. Having established how we manage nuisance factors through blocking and randomization, let us now examine the fundamental principle underlying the blocking strategy. The core idea is elegantly simple. By organizing our experimental units into blocks, we create groups that are internally homogeneous. Within each block, the experimental units are substantially similar to one another, which means any differences we observe between treatments cannot be attributed to variation within the block itself. This homogeneity allows us to isolate treatment effects more precisely. By removing the variability that would otherwise exist among different block levels, we substantially increase the accuracy and sensitivity of our treatment comparisons. In essence, blocking acts as a statistical filter, allowing the true treatment differences to emerge more clearly from the experimental noise. Now that we understand how blocking improves our experimental precision by creating homogeneous units, we must recognize an important consequence. Blocking necessarily restricts our randomization scheme. Rather than randomizing all treatment combinations across the entire experiment, we randomize only within each block. All test conditions in one block must be completed before moving to the next block. Consider a practical example. If an experiment requires 2 days to run, all runs scheduled for day 1 are executed completely before any runs begin on day 2. This temporal constraint is a restriction on randomization. However, within each individual block, we maintain randomization of the treatment assignments. This hybrid approach balances practical necessity with statistical rigor, ensuring that block-to-block variability doesn't confound our treatment comparisons while still preserving randomization where it matters most. Having established that blocking restricts randomization, we must now address a critical statistical consequence. The block effect itself is not a factor of interest in our analysis. We deliberately exclude it from significance testing because the blocking structure violates the fundamental assumptions required for constructing a valid F-test. Since blocks are not randomly assigned, they represent a necessary constraint imposed by practical experimental limitations. The independence and homogeneity assumptions underlying standard hypothesis tests do not hold. This distinction is essential. We use blocks to reduce experimental error and improve precision, but we do not treat them as treatments worthy of statistical inference. Instead, we account for their variability in our error structure while focusing our hypothesis tests exclusively on the treatment effects themselves. Having established that we cannot formally test the block effect itself, we now turn to the structure that makes blocking valuable, the randomized complete block design. In this framework, we partition our total experimental units into blocks, with each block containing every treatment combination replicated identically. The term complete carries specific meaning. It guarantees that no treatment combination is missing from any block. This balanced structure is essential because it allows us to isolate and remove block-to-block variation from our error term, thereby increasing the precision of our treatment comparisons. The design achieves this through systematic replication across blocks rather than through randomization of the blocks themselves. This distinction is crucial. We control block effects through design structure, not through statistical testing. In our next example, we'll see how this principle applies concretely to a practical measurement problem where blocking becomes instrumental in detecting true differences among treatments. Now we turn to a concrete application of the randomized complete block design framework, the hardness testing example. Our research question is straightforward. We want to determine whether 4 different tips produce different mean hardness readings when used on a Rockwell hardness tester. The experimental units here are test coupons, and we assign each tip to measure hardness on these coupons. However, the coupons themselves represent a significant source of nuisance variability. Different coupons may have inherent differences in their material properties that affect hardness readings, independent of which tip we use. This is precisely the type of systematic variation that blocking helps us control. Rather than treating coupon differences as random noise, we can structure our experiment to account for this variation explicitly through the block design framework. To implement this experiment as a randomized complete block design, we assign all 4 tips to each test coupon. Each coupon functions as what we call a block, essentially a more homogeneous experimental unit on which we can test all treatments. The key insight here is that while variability between different blocks may be substantial, the variability within a single block should be relatively small. In general terms, a block represents a specific level of our nuisance factor. By structuring the experiment this way, we can isolate and account for the effects of the blocking factor, allowing us to focus on detecting true differences among the tip treatments. This two-way structure, with both tips and blocks as factors, requires us to partition the total variability appropriately when we conduct our statistical analysis. Now we observe the two-way structure that emerges from our randomized complete block design. We have 4 blocks, our coupons, and within each block we apply all 4 tips. This creates a rectangular array of observations where treatments appear in columns and blocks appear in rows. The critical insight is that we're still testing whether the treatment means are equal, but we must now account for block-to-block variability. The blocks represent our nuisance factor, the inherent differences between coupons. By including blocks in our analysis, we isolate and remove their contribution to the overall variation, leaving us with a cleaner estimate of the treatment effect. This blocking strategy increases the precision of our treatment comparisons. The variation we observe within each block is typically much smaller than variation across blocks, so by controlling for blocks, we substantially reduce the noise in our experiment and strengthen our ability to detect true differences among the hardness testing tips. Now we formalize the randomized complete block design model. Each observation can be decomposed into 4 additive components. First, we have the overall mean, which represents the baseline level common to all measurements. Second, we include the treatment effect, which captures the difference attributable to which specific treatment was applied. Third, we incorporate the block effect, representing the systematic variation introduced by the blocking factor. In our hardness testing example, This would be the differences between the 4 blocks of material. Finally, we account for random error, the unexplained variation that remains after removing both treatment and block effects. This decomposition is fundamental because it allows us to isolate the treatment effects of interest while explicitly controlling for the known source of variation represented by the blocks. This structured approach increases our statistical power to detect true treatment differences. Having established the structure of the randomized complete block design model with its treatment effects, block effects, and random error components, we must now examine the foundational assumptions that validate our statistical inferences. The random error term in our model must satisfy several critical conditions. First, the errors are assumed to be independently distributed, meaning the error in one observation does not influence errors in other observations. Second, they follow a normal distribution, which ensures the validity of our hypothesis tests and confidence intervals. Third, the errors maintain constant variance across all treatment and block combinations, a property known as homogeneity of variance. These assumptions are not merely mathematical conveniences. They are essential for the reliability of our significance tests and the validity of our conclusions about treatment differences. When these assumptions hold, we can proceed with confidence to test whether observed differences among treatment means reflect genuine treatment effects or merely random variation. This brings us naturally to our next consideration: the equivalent ways of formulating our hypotheses about treatment effects. Having established our random error assumptions, we now turn to an important conceptual equivalence. The hypothesis tests we conduct in this model can be formulated in 2 mathematically equivalent ways. First, we can frame our hypotheses in terms of the treatment means, testing whether the population means across our treatment groups are equal. Alternatively, we can express identical hypotheses using treatment effects, which represent deviations from the overall mean. These 2 formulations are completely equivalent. They simply provide different perspectives on the same underlying question. Whether you think about comparing means directly or examining whether treatment effects are 0, you arrive at identical conclusions. This flexibility in formulation proves useful depending on the context and interpretation we wish to emphasize. Next, we'll examine how to verify that our model adequately captures the data structure. Having established the equivalence between testing means and testing effects, we now turn to validating our model assumptions. Model adequacy assessment follows the standard diagnostic procedures you've encountered throughout this course. We examine residual plots, normality tests, and homogeneity of variance as usual. However, when working with block designs, there is one critical additional step. We must inspect the residuals plotted against the block variable itself. This diagnostic reveals whether the blocking factor has been properly accounted for in our model. If systematic patterns emerge in this plot, it suggests the blocking structure may not have adequately captured the variation we intended to eliminate. Conversely, random scatter indicates the blocks have successfully isolated extraneous variation. This verification ensures our model specification is appropriate before proceeding to formal hypothesis testing. Now we turn to the analysis of variance framework itself. Having verified our model assumptions through residual diagnostics, including the critical check of residuals against the block variable, we proceed to partition the total variation in our response into meaningful components. The ANOVA table decomposes the sum of squares into treatment effects, block effects, and residual error. This decomposition allows us to construct f-statistics that test whether treatment differences are statistically significant relative to the background noise in our experiment. The key insight is that blocking reduces the error term by removing systematic variation attributable to the blocking factor, thereby increasing our power to detect true treatment effects. We'll examine how these sums of squares combine and what their ratios tell us about the significance of our results. We now turn our attention to the error component in analysis of variance. Recall that the fundamental additive property of ANOVA decomposes total variation into systematic components attributable to treatments and blocks, plus residual error. This error term represents the unexplained variation in our data, the deviations that remain after accounting for treatment and block effects. The sum of squared errors, denoted SSE, captures this residual variation and serves as our baseline for assessing whether treatment differences are statistically meaningful. In the next slide, we will see how these error calculations integrate into the complete ANOVA table, where we compute mean squares and f-statistics to test our hypotheses about treatment effects. Now we construct the ANOVA table, which organizes all our calculations into a standard format. Each row represents a source of variation, treatments, blocks, and error. For each source, we calculate the sum of squares, which measures total variation from that source. We then divide by the appropriate degrees of freedom to obtain mean squares, which are variance estimates. The test statistic for treatments is the ratio of the treatment mean square to the error mean square. Notice that we do not test the block effect directly, but the block mean square provides valuable diagnostic information. By comparing the block mean square to the error mean square, we can assess whether blocking was effective. If the block mean square substantially exceeds the error mean square, blocking successfully reduced unexplained variation. Conversely, if error variation is larger than block variation, the blocking strategy may have actually reduced our statistical power. This comparison guides our decision about whether the blocking design was worthwhile for future experiments. Now that we have constructed our ANOVA table, we must evaluate whether blocking was actually beneficial. The key comparison is between the mean square for blocks and the mean square for error. If the block mean square exceeds the error mean square, then our blocking strategy successfully reduced unexplained variation in our data. This reduction strengthens our hypothesis tests and narrows our confidence intervals for treatment comparisons. Conversely, if the error mean square is larger than the block mean square, the blocking has been counterproductive. In this scenario, we have essentially wasted degrees of freedom on blocks that do not capture meaningful variation, thereby reducing the power of our statistical tests and widening our confidence intervals. Therefore, the comparison of these two mean squares tells us whether our experimental design choice was justified. We now turn to situations where either treatments or blocks, or indeed both, may be classified as random effects rather than fixed effects. The fundamental analytical procedures remain unchanged. However, the interpretation of our results shifts considerably. When blocks are treated as random, we make an important assumption. The differences we observe among treatments should remain consistent across the entire population of blocks we might have selected. This assumption allows us to generalize our treatment comparisons beyond the specific blocks in our experiment. Additionally, the expected mean square for the block effect takes on a different form when blocks are random, which affects how we construct our test statistics and confidence intervals. This distinction between fixed and random effects is crucial for proper inference, as it determines what population our conclusions apply to and how we should interpret the variability we observe in our data. Now we turn to a practical application that illustrates the randomized block design in action. A laboratory is evaluating 3 different washing solutions for their ability to inhibit bacterial growth in 5-gallon milk containers. The experimental constraint here is critical. Only 3 trials can be conducted per day. This limitation motivates the use of blocking by day, since daily conditions, temperature, humidity, or other environmental factors could introduce systematic variability into the results. Over 4 consecutive days, the researchers applied each of the 3 solutions once per day, generating a complete replicate of the experiment. Our task is to analyze this data using a significance level of 0.05 and determine whether the washing solutions differ meaningfully in their effectiveness. Notice how the blocking structure addresses a practical constraint while simultaneously controlling for a known source of variation. This is precisely the strength of the randomized block design in real-world experimentation. Here we have the experimental data collected across the 3 washing solutions and 4 days. Each cell represents the bacterial count observed under those specific conditions. Notice the general trend. Bacterial growth increases substantially from day 1 through day 4, regardless of which solution is used. Solution 3 appears to show the lowest counts overall, suggesting superior effectiveness at retarding bacterial growth. Solutions 1 and 2 show higher counts, particularly by day 4. This raw data will now be analyzed using the randomized block design framework, where days serve as blocks to account for the temporal variability the experimenter anticipated. The analysis of variance will partition the total variation into components attributable to the solutions themselves, the day effects, and random error, allowing us to determine whether the differences we observe among solutions are statistically significant. We now fit a general linear model to the experimental data from the previous slide, treating both solutions and days as fixed factors. The model includes 3 solution types and 4 time points, giving us 12 total observations. The analysis of variance table reveals the statistical significance of each factor. The solutions factor yields an F-statistic of 40.72 with a p-value essentially equal to 0, indicating highly significant differences among the 3 solutions. Similarly, days shows an F-statistic of 42.71 with p-value near 0, demonstrating that time is a highly significant predictor of the response variable. The model explains 97.22% of the total variation in our data, which is exceptionally strong. The adjusted R-squared value of 94.9% accounts for the number of parameters estimated and confirms the model's excellent fit. The residual sum of squares of 51.83 on 6 degrees of freedom gives us a mean squared error of 8.64, which serves as our estimate of experimental noise. This relatively small error term supports our conclusion that both factors are genuinely influential. However, this analysis assumes we have adequately controlled all sources of variation. The next question becomes more complex. What if additional nuisance factors are present in our experimental design? We've just examined a 2-factor design with solutions and days, where both factors were of primary interest. But experimental situations frequently involve multiple nuisance factors, variables that we must account for statistically but don't directly care about. The question becomes, how do we design and analyze experiments when we have more than one such nuisance factor? This is a critical practical problem in experimental design. Consider a realistic scenario. Suppose we're investigating 5 different propellant formulations for aircraft escape systems, and we want to measure their burning rates. However, the raw materials come from different batches, and different operators with varying skill levels prepare these batches. Both operator experience and batch variation represent nuisance factors that could substantially affect our measurements. We cannot ignore these sources of variation, yet they're not the focus of our investigation. The question then is, how do we structure our experimental design to isolate the effects of the propellants while controlling for these multiple nuisance factors? This requires a more sophisticated blocking strategy than we've previously considered. Building on our discussion of multiple nuisance factors, let's examine a concrete experimental scenario. Consider an engineer investigating 5 different propellant formulations for aircraft escape systems, measuring their burning rates. The complication here is that raw materials come from different batches, and these batches are prepared by operators with varying levels of skill and experience. This creates 2 distinct nuisance factors simultaneously: operator variability and batch-to-batch variation in raw materials. Both of these factors could influence our burning rate measurements, potentially confounding our conclusions about the propellant formulations themselves. The critical question becomes how we design our experiment to isolate the effects of our primary treatment, the propellant type, while accounting for these 2 sources of unwanted variation. This is precisely the kind of practical problem where careful experimental design becomes essential to obtaining valid results. Now we need to formalize our experimental approach to this rocket propellant problem. We have identified 2 nuisance factors, operator skill and raw material batch variability, that could confound our results if left uncontrolled. Rather than treating these as random noise, we'll incorporate them directly into our experimental design through blocking. This strategy allows us to isolate the effects of our 5 propellant formulations while accounting for systematic variation introduced by different operators and material batches. By structuring our experiment this way, we can obtain precise estimates of treatment effects without requiring an excessive number of observations. This leads us naturally to consider row-column designs, which provide an elegant framework for managing multiple blocking factors simultaneously while maintaining experimental efficiency. Having addressed the propellant problem, we now turn to row-column designs, a powerful framework for managing 2 blocking factors simultaneously. These designs operate under a critical assumption: the 2 blocking factors do not interact with one another. This assumption is crucial because it permits us to construct efficient designs requiring only a single observation per combination of blocking factor levels. The structure is elegantly simple. We arrange our design as a 2-dimensional array where one blocking factor defines the rows and the other defines the columns. Each cell in this array receives exactly 1 treatment label. This arrangement dramatically reduces the number of observations needed compared to designs without blocking. the efficiency gain is substantial. By leveraging the structure of both blocking factors, we extract maximum information from minimal data. This becomes particularly valuable when observations are expensive or time-consuming to obtain. With our design structure established, we must now address the practical implementation. We need to select our experimental plan and then randomly assign treatment labels to the blocking factor levels. This randomization step ensures that our inferences remain valid and unbiased. Having established the fundamental structure of row-column designs with their two non-interacting blocking factors, we now turn to the practical implementation of such experiments. The design phase requires two critical decisions. First, we must select an appropriate experimental plan, a structured framework that will govern how treatments are assigned across our row and column blocks. Second, we need to randomly allocate treatment labels to the actual levels of both our treatment factor and our blocking factors. This randomization step is essential for ensuring that our experimental inferences remain valid and unbiased. The specific plan we choose will depend on the number of rows, columns, and treatments available to us. In the next section, we'll examine one particularly elegant solution to this design problem: the Latin Square design, which imposes a special structure ensuring balanced representation across all dimensions of our experiment. Having established our experimental framework, we now turn to a specific design structure called the Latin Square. This is an abaya design, meaning we have a rows and a columns, where a represents the number of treatment levels. The defining characteristic is that each treatment letter appears exactly once in every row and exactly once in every column. This orthogonal structure is powerful because it allows us to control for two blocking factors simultaneously. Units within the same row are homogeneous, as are units within the same column. However, units in different rows and different columns are substantially different from one another. This design is particularly valuable when you have two sources of variation you wish to eliminate, such as spatial gradients in two directions or temporal and environmental factors. The Latin Square elegantly balances treatment assignments across both blocking dimensions, ensuring that no treatment is confounded with either blocking factor. Having established the fundamental structure of Latin Square designs, we now turn our attention to the specific configurations that appear most frequently in practical applications. While the theoretical framework permits numerous arrangements of letters across rows and columns, certain designs have proven particularly useful and are therefore standardized in experimental practice. These common designs serve as templates that researchers can readily implement and adapt to their particular experimental contexts. In the next section, we will examine standard Latin Square designs more closely, particularly those where the first row and first column follow alphabetical ordering. This standardization facilitates both the construction of experimental designs and the communication of results across different studies. Understanding these conventional patterns is essential before considering more complex scenarios, such as situations where the number of treatment levels does not align perfectly with the blocking structure. Standard Latin Square designs possess a particular structure that makes them especially useful as starting points for experimental planning. In these designs, the letters representing our treatment levels appear in alphabetical order both in the first row and in the first column. This standardized arrangement provides a convenient reference framework from which we can generate variations suited to our specific experimental needs. The practical workflow typically proceeds as follows. We begin by selecting a standard design appropriate to our number of treatment levels, and then we systematically assign our actual treatment labels to the letters in that standard structure. This two-step approach simplifies the design selection process considerably. However, experimental reality sometimes presents constraints that complicate our planning. The question naturally arises, what should we do when we cannot obtain exactly a levels for one of our blocking factors? This situation leads us to consider alternative designs that maintain the desirable properties of Latin squares while accommodating unequal block sizes. One such alternative is the Youden design, which we will examine next. We now turn to Youden designs, which represent an elegant solution when we face practical constraints in experimental blocking. Recall that standard Latin squares require equal numbers of levels for both blocking factors. However, real-world experiments often impose restrictions on one blocking dimension. Perhaps we can only accommodate fewer column blocks than we have treatments. A Youden design accommodates this situation by arranging treatments across B row blocks and G column blocks. where G is strictly less than A. The key principle remains. Experimental units within the same row or column block are homogeneous, while units in different rows and columns are substantially different. Each treatment appears exactly G times in the design, once in each column block and distributed across the row blocks. This structure preserves the orthogonality properties we value while adapting to practical constraints. In the next slide, we'll examine a concrete 4x3 example that illustrates how this design operates in practice. Youden designs become particularly valuable when practical constraints limit our blocking capacity. Specifically, we employ this design when one blocking factor can accommodate fewer experimental units than the total number of treatments we wish to compare. Rather than abandoning our two-way blocking structure, the Youden design elegantly accommodates this restriction. The 4x3 example illustrated here demonstrates this principle concretely. We have 4 treatments and 3 column blocks, which is fewer than our treatment count. This design maintains the orthogonality and balance properties we value while respecting real-world limitations on block size. Each treatment still appears exactly once within each row block and once within each column block, preserving the blocking efficiency we seek. This approach proves invaluable in agricultural experiments, industrial settings, and other contexts where experimental units cannot be freely arranged into arbitrarily large blocks. Having examined Youden designs where block size constraints limit our options, we now turn to a more flexible approach: replicated row-column designs. These designs extend the row-column structure by replicating the entire design framework multiple times. Specifically, we combine separate row-column designs into a single comprehensive design. This replication strategy requires that either our columns or rows accommodate a total size of G times S, where G represents the dimension of each individual design unit and S denotes the number of replications. A practical illustration of this method involves stacking multiple Latin square designs vertically, creating a layered structure that maintains the orthogonal properties of each component while increasing our overall experimental capacity. This approach proves particularly valuable when we need to balance experimental constraints with the desire for increased replication and statistical power. Building on our discussion of replicated row-column designs, we now examine a concrete example using 2 replications of a 3x3 Latin square. This configuration provides a practical illustration of how multiple Latin squares can be stacked to create a more robust experimental structure. By replicating the design, we gain increased precision in our estimates while maintaining the orthogonal balance that makes Latin squares so valuable. The 2x3x3 structure allows us to control variation across both rows and columns simultaneously, while the replication dimension adds another layer of experimental control. This design bridges our conceptual understanding of single Latin squares with the more complex row-column models we'll develop next, where we'll formally specify the statistical framework underlying these arrangements. Building on the 2x2 Latin square design we just examined, we now move to the more general row-column design framework. The statistical model for this design incorporates 3 sources of systematic variation beyond treatment effects: row effects, column effects, and treatment effects, all combined additively with random error. This additive structure is crucial because it allows us to partition the total variation in our data into independent components. Each observation is modeled as the grand mean plus a row effect, plus a column effect, plus a treatment effect, plus random error. The assumption of additivity means there are no interaction effects between rows, columns, and treatments. This simplification enables us to construct an analysis of variance table that cleanly separates the sum of squares and degrees of freedom into distinct components for rows, columns, treatments, and error. This partitioning forms the foundation for hypothesis testing in the subsequent ANOVA framework. Having established our additive statistical model for row-column designs, we now turn to the analysis of variance framework. The fundamental principle here is partitioning total variation into meaningful components. We decompose the total sum of squares and total degrees of freedom across our observations into 4 distinct sources: variation attributable to rows, variation attributable to columns, variation due to our treatment factor, and finally, residual error. This decomposition allows us to isolate the treatment effect while accounting for systematic variation from both blocking factors. Each component carries its own degrees of freedom, determined by the number of levels in each factor. This structured partition forms the foundation for hypothesis testing and inference on treatment effects, which we'll address in the next section. Having partitioned our total sum of squares and degrees of freedom across rows, columns, treatments, and error, we now turn to the critical step of validating our model assumptions. Before we can confidently construct confidence intervals or conduct hypothesis tests on treatment contrasts, we must examine the residuals carefully. Specifically, we should plot residuals against both row and column block factors to ensure that blocking has effectively removed systematic variation and that no unexpected patterns remain. Once we've confirmed that our assumptions are reasonably satisfied, we proceed with standard inference procedures. We can then construct confidence intervals and perform hypothesis tests on contrasts among treatment means using the familiar t-distribution framework. This brings us to our concrete application, the rocket propellant problem, where we'll investigate whether different propellant types produce significantly different performance outcomes. We now turn to a practical application, the rocket propellant problem. Our research question is straightforward. Do different propellant types produce significantly different responses? And if differences exist, which specific types differ from one another? We'll conduct our analysis at the conventional significance level of alpha equals 0.05. This is a two-stage investigation. First, we test whether propellant type has any effect at all using analysis of variance. Second, should we reject the null hypothesis, we proceed to pairwise comparisons to identify which propellant types are meaningfully distinct. The experimental design accounts for two blocking factors, batch and operator, which we've already verified satisfy our model assumptions through residual diagnostics. With these controls in place, we can now isolate the treatment effect of propellant type and make reliable inferences about differences among the four types under investigation. Examining our analysis of variance results, we find compelling evidence that propellant type significantly affects rocket response. The F-statistic for type equals 7.73 with a p-value of 0.003, well below our significance threshold of 0.05. This means we reject the null hypothesis of equal means across propellant types. The model explains approximately 81% of the total variation, indicating a reasonably strong fit. Now we must identify which specific propellant types differ meaningfully. The subsequent pairwise comparisons employ a multiple comparison procedure to control for inflated error rates. Notice that type B differs significantly from type A, with a mean difference of negative 8.4 units and a p-value of 0.011. Similarly, types D and B show a substantial difference of 9.6 units with p-value 0.0042. Type D also differs significantly from type C by 7.4 units at p-value 0.0254. These three comparisons remain statistically significant after adjustment. Therefore, propellant types B and D emerge as distinctly different performers, suggesting practical implications for rocket design selection. Now we examine the pairwise comparisons between all type groups using Tukey's honest significant difference test. Each row represents a comparison between two types, showing us the estimated difference in means, the standard error of that difference, the test statistic, and the corresponding p-value. Notice that we're conducting multiple comparisons simultaneously, which is why we use this adjusted procedure rather than individual t-tests. The standard error remains constant at approximately 2.07 across all comparisons because we have balanced sample sizes. We identify statistically significant differences by examining p-values less than our significance level. Three pairs emerge as significantly different: type B versus type A with a p-value of 0.0111, type D versus type B with a p-value of 0.0042, and type D versus type C with a p-value of 0.0254. These results indicate that type D produces substantially different response values compared to both B and C, while type B also differs meaningfully from type A. Based on our pairwise comparisons using Tukey's adjustment for multiple testing, we can now draw our conclusions. Three specific pairs of treatment means demonstrate statistically significant differences at the alpha equals 0.01 significance level. Specifically, the difference between B and A is significant, as is the difference between D and B, and finally the difference between D and C. All other pairwise comparisons fail to reach statistical significance at this stringent threshold. Notice that the p-values for these three comparisons, 0.0111, 0.0042, and 0.0254 respectively, all fall below our critical value. This tells us that these particular signal sequences produce meaningfully different outcomes. The remaining comparisons, while some show moderate differences in means, do not provide sufficient evidence to conclude true population differences exist. Now let's apply this methodology to a practical example involving traffic signal optimization. We now turn to a practical application involving traffic signal optimization. Researchers designed an experiment to evaluate 5 different signal sequences, labeled A through E, based on their efficiency in minimizing and used red light time. The study employed a randomized block design, measuring and used red light duration across 5 intersections during 4 distinct time periods. This experimental structure allows us to control for both spatial and temporal variation that might otherwise confound our results. Our research question is twofold. First, do these signal sequences produce statistically significant differences in performance? And second, if differences exist, which specific pairs of sequences differ meaningfully from one another? We will test these hypotheses at the 0.01 significance level using SAS software. The data table on the next slide presents the unused red light measurements in seconds for each intersection time period combination. Notice that each signal sequence appears exactly once in each row and column, confirming the balanced design of this experiment. This structure is essential for conducting a valid analysis of variance and subsequent pairwise comparisons. We now have our experimental data organized in a Latin Square design, where each traffic light sequence appears exactly once at each intersection and in each time period. This balanced structure controls for both spatial and temporal variation in the data. The response variable represents unused red light time measured in seconds across our 5 sequences labeled A through E. Notice that the data is complete with no missing observations, which is essential for the validity of our analysis. Before we interpret the results on the next slide, I want to emphasize that we have a 2-factor blocking design here. The intersections and time periods serve as blocking factors to reduce experimental error and increase the precision of our comparison among the 5 signal sequences. This design choice is particularly important in traffic engineering studies where environmental conditions vary significantly across locations and times of day. We now turn to the general linear model analysis of our experimental data. Our design incorporates 3 factors: intersection location, time period, and sequence assignment. The analysis of variance table reveals critical findings about which factors meaningfully influence our response variable. The intersection factor shows no significant effect, with a p-value of 0.964, indicating that location differences are negligible. Conversely, time period demonstrates overwhelming statistical significance with a p-value approaching 0 and an f-statistic of 62.11. This tells us that temporal variation dominates our response patterns. The sequence factor approaches marginal significance at p equals 0.135, suggesting a potential but inconclusive effect. With 8 degrees of freedom in our error term and a residual sum of squares of 45.15, our model captures substantial variation in the data. This analysis establishes our baseline understanding. However, we face a methodological question as we contemplate extending this framework. What analytical strategies become necessary when we incorporate additional blocking variables beyond these 3 factors? We've just examined a Latin Square design with 2 blocking variables, intersection and time period, while applying 5 different treatment sequences. The analysis revealed that time period has a highly significant effect on our response variable, whereas intersection and sequence do not. But experimental situations frequently demand control over 3 sources of nuisance variation rather than merely 2. This raises an important methodological question. How do we extend our blocking strategy to accommodate an additional blocking factor? The Latin Square design, while powerful for 2 blocking variables, reaches its limit. To address this challenge, we turn to a more sophisticated approach: the Graeco Latin Square design. This method superimposes a second Latin square onto the first, enabling us to simultaneously control variation across 3 distinct blocking dimensions. The analytical framework remains conceptually similar to what we've already learned, but with the added complexity of managing three orthogonal blocking structures. Let's explore how this extension works and what it offers us in terms of experimental efficiency and precision. Having established the Latin square design for controlling two blocking variables, we now extend this framework to accommodate three sources of nuisance variation. The Graeco Latin square accomplishes this by superimposing a second Latin square onto the first, where the second square uses Greek letters rather than Latin letters to denote the third blocking factor. This elegant construction maintains the orthogonal structure essential for balanced experimental designs. The analytical approach parallels that of the standard Latin square, though we now partition the sum of squares to account for an additional blocking variable. This design proves particularly valuable in industrial and agricultural experiments where controlling multiple environmental or contextual factors simultaneously is critical to isolating treatment effects with precision. Now we examine a concrete example of a 4x4 Graeco Latin square design. This particular configuration demonstrates how we simultaneously control three blocking variables while testing a single treatment factor across 4 levels. Notice the structure. Rows represent one blocking dimension, columns represent a second blocking dimension, and the Greek letters superimposed on the Latin letters represent the third blocking variable. Each treatment level appears exactly once in every row, every column, and every Greek letter category. This orthogonal arrangement ensures balanced control of nuisance variation across all 3 dimensions. The table illustrates the practical implementation of the theoretical framework we discussed previously, showing how researchers can efficiently allocate experimental units while maintaining statistical rigor across multiple sources of potential confounding variation. The Graeco Latin square design incorporates a linear statistical model that decomposes the observed response into several additive components. Each observation is expressed as the overall mean plus 4 distinct sources of variation. First, we have the treatment effect, which captures the impact of the experimental treatment being applied. Second, the row effect accounts for systematic differences across rows in the design structure. Third, the column effect represents variation attributable to columns. Fourth, the block effect, specifically the third blocking factor, captures additional systematic variation from the 3-dimensional blocking structure inherent in the Graeco Latin arrangement. Finally, we include a random error term that represents unexplained variation or noise in the measurements. This decomposition allows us to isolate and estimate each source of variation independently, which is precisely why the Graeco Latin square is so valuable for controlling multiple nuisance factors simultaneously while maintaining experimental efficiency.